Hi friends, today we are going to see properties of DFT. So let us see what are properties of DFT, which is Discrete Fourier Transform. So the first property, that let us list the first property as linearity property. So the first property that we are going to see is a linearity property. Now what does linearity property says that if I have x of n whose DFT if I calculate gives me x of k, right? So when I have a n point x of n, I am going to get an n point x of k. Now suppose I have two functions. So let us say, suppose I have two functions which is x1 of n whose DFT is x1 of k and x2 of n whose DFT is x2 of k. And then suppose if I have a function a x1 of n plus b x2 of n. Now what will be its DFT? Okay, so I have two functions x1 of n, x2 of n. Its DFT individually is x1 of k, x2 of k. Then suppose if I have a combination of x1 of n and x2 of n with a scaling factor of a and b, then what will be this function's DFT? So the linearity property says that its DFT is a x1 of k plus b x2 of k. That means a, which is a scaling factor or a constant, is as it is multiplied by x1 of k, which is nothing but DFT of x1 of n, plus a constant b multiplied by the DFT of x2 of n. Okay, so the linearity property is whenever I have an addition, the DFT operator will be distributed over addition. That means I will get individual DFTs ka addition. Okay, so that is nothing but the linearity property. Let us go for the second property. The second property says as periodicity property. Now for periodicity property, it says before directly entering the periodicity property, let me explain you what you mean by periodic signal. So let us say that I have a signal x of n which is 1, 2, 3, 4, and I say this signal to be periodic. Okay, so let us graphically see how this signal looks like. So graphically, when I draw the signal, I have this as n, this as my x of n, that is a function, and let us say this is my n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. Similar way, I will have n is equal to minus 1, n is equal to minus 2, n is equal to minus 3, and n is equal to minus 4, and so on. And here also so on till infinity. Now how the signal will look like? For n is equal to 0, the value is given as 1. So I have the value, amplitude value as 1 for n is equal to 0. Then for n is equal to 1, the value is given as 2. So let us say it is a bit rising up. So this is value is 2. Then for n is equal to 2, the value is 3. So it is further rising up, and this is 3. finally for n is equal to 3, my value is given as 4. So instead of writing here, I write here 4. Now when I say the signal is periodic, it means that the next number, okay, that is for n is equal to 4, I will repeat what is that n is equal to 0. So my value will be same as that of 1, right? Then I will have n is equal to at 5, let us say 5, I will have n is equal to, at n is equal to 5, I have the amplitude as 2, and so on. So it is a never ending signal, okay. Similar way it will be in the negative side. Now at -1, the last sample before 1 is 4, so the last sample over 1 will be before 1 is 4. Then I will have 3, then we will have 2, and finally we will have 1, and this will also be ever going. It will never end. So this is my periodic signal. Now when we define a periodic signal, graphically, when I say that x of n is equal to x of n equals to 1, 2, 3, 4, when I say this, I mean that I only will see this portion of the signal. We will only observe this portion of the signal because this portion is going to repeat every interval of 4. So the period of the signal is as 4. Okay. Now, so when I say that a periodic signal, I will only open this window and see what happens in this window. So when I say periodic signal, we will only see the signal through a window, and that window has to be specified. Okay. That window could be from 0 to 3. Now if I shift, it will be 1 to 4 and so on. But that window should be specified. When I say the signal is periodic with period 4, it means the window is specified from 0 to 3. That has been there. So this is what a representation or visualization of a periodic signal. If I dump a sample of periodic signal, for example, I say that x of n minus 1, then I will dump a value from this side because I'm going to shift the signal or delay the signal by one value. So the whole signal will get shifted. Window is not shifting, internal signal is shifting. So the whole new signal will be, the 4 will come at the 1's place, 1 will come at the 2's place, 2 will come at the 3's place, and 3 will come on the 4's place, and 4th will be dumped out. So every time when I shift in this side, I will dump one value out of window, but I will take new values in from this side. Similar way, when you slide the signal on that side, I will dump the signal from this side, whereas I pick up new signal from this end. So if I ask you a question that what is x of 5 in the above case, so you can immediately say that x of 5 is similar to that of x of 1, right? So I can say that x of 5 is equal to x of 1. Have I got that? Or you can say that x of 1 is equal to x of 5, any which ways. So I can say that in general we can write it like x of n plus n equals to x of n. For example, if I write x of 1 plus 5, or if I write x of 5 plus is equal to 1. So we know that here in this case capital N is 4 and I want 5. So it is plus 1, which is nothing but equal to x of 1. So when I say a signal is periodic, it should satisfy this condition. Okay, so every periodic signal, discrete periodic signal, will satisfy this condition. That is x of n plus capital N is equal to x of n. So where this capital N is nothing but your period. Okay, so from this you can easily see that it is x of 5 equals to x of 1. And in this way you can go on finding the other factors. Like suppose I want x of minus 1. Okay, let us say that I want x of minus 1. So small n is minus 1 plus 4 equals to x of minus 1. So you get x of minus 4 plus minus 1 plus 4 is 3 equals to x of minus 1. So x of minus 1 is equal to x of 3. So x of 3 can be replicated at x of minus 1. And you can say vice versa, that is x of minus 1 equals to x of minus 3, because they are equal, right? So this is how every periodic signal should satisfy a condition. Okay, now we can go for a periodicity property. Now the periodicity property says that if I have, so let us say my periodicity property, it says that suppose I have, if I have x of n whose DFT is x of k, and I say that a newly introduced function that my x of n is periodic. So let us say it satisfies this condition. Then my x of k will also be periodic. That means it will also satisfy this condition. Okay, so whenever I say that the input signal is periodic, the output or the Fourier transformed signal is also periodic. That is a periodicity property, which is number 2. Let us go to third property, time reversal property. So we are going to take today a new property in DFT which is called as time reversal property. Now time reversal property states that if suppose I have a signal x of n whose DFT is x of k, then if I reverse the signal, that is x of minus n, then what will be its DFT? So we wanted to know that if suppose we mirror the signal x of n, then what will be the output signal, or what will be the transform of that signal. So let us first understand what do you mean by mirroring of a signal or folding of a signal. If I have a signal called x of n, which is 1, 2, 3, 4, then if I draw the signal will look like, this is my n, this is my x of n, then my signal will look like 1 units, 2 units, 3 units and 4 units, with 0, 1, 2, 3 is my n and the amplitude is 1, 2, 3 and 4. Okay, now this is my x of n signal. Now how my x of minus n signal will look like, or what will be the signal? Assuming that the given signal is periodic, this signal will repeat itself after 3. That means at n is equal to 4, I will have 1 again. At n is equal to 5, I will have 2 again, and so on. In similar fashion, if I see at the negative side, I will see a 4 at n is equal to minus 1. Then I will see a minus 2 at minus 2, the value of the amplitude as 3, and so on and so forth. So this is an infinite length sequence in both the sides. Now whenever we look at periodic signal, we always look into a window, which we called it as the fundamental period of the signal. So for the current signal, the window is 3, or total number of samples are 4. So the period is 4. So we called it as a capital N is equal to 4. Now whenever we do any kind of transformation with periodic signal, we always see what happens inside this window. Folding a signal or mirror imaging a signal is keeping the 0th sample as it is and transforming all the positive index n samples to negative index and negative index n sample to positive index. So I'll be taking up these samples and reflecting on the other side of the y-axis, and whatever there on the other side of the y-axis will be reflected back on the x-axis, on the positive n index of the y-axis. Now I'll keep 0 as it is, and the sample 2 will be replaced by n is equal to -1 sample. N is equal to 2 will be replaced by n is equal to -2 sample, and n is equal to 3 will be replaced by n is equal to -3 sample. So in this way there will be all the samples will be mirrored. So these samples will go on the other side of this signal, other side of the y-axis, whereas the other side of the y-axis signals will come on replicate on this side of the signal. So the new signal will look like, if I see, now this is my n, but now this sample is x of -n. Then my new sample will look like 1 will not leave its place, so 1 will be as it is. -1 takes +1's place, so it is 4. So now the amplitude of the second sequence is 4, whereas second has changed with 3 only, so it is 3 again. And the last sample has been converted to 2. So my x of -n is 1, 4, 3 and 2. So what I did was, I kept the first position as it is, replaced these samples about n is equal to 3. So what happened was, because the sample set of sample was even, leaving n is equal to 0 gives me odd number, and then when I interchange, I keep one sample as it is, and about that sample I will replicate the samples. So the mirror image will look like 1, 4, 3, 2 of x of n. So x of -n is as good as changing the position of 4, which was previously at 3, to 1. That means I can similarly write as x of -n as capital N minus small n, where here the capital N is 4. So 4 minus 3, that is a position of 3, will give me 1. That is x of 1. So position of the third position is interchanged with the first position. The third position, or the second position will remain with the second position, and the third position will be shifted with the first position. So I can also write x of -n as x of n minus n, since the signals are periodic with period capital N. Okay, so that means if I transform, or if I will shift or fold a signal which is periodic with period n, it can be written as x of n minus small n, where this n is the period of signal. Then DFT of such signal is x of minus k with period n, or I can write as x of n minus k. That means if I fold a time sequence, then my frequency will also get folded. So reversing a signal in time domain, reverse the signal in the frequency domain also. So if I have x of n minus n signal, then I will have x of n minus k signal with me. This is the time reversal property. Now, in time shift property, I'm saying that let this signal be a periodic signal. So if this signal is a periodic signal, then it is going to be infinite to infinite, and I'm going to observe the signal only in this window. So when I'm going to shift the time either in left or right side, that is, I'm going to shift the signal this way, or I'm going to shift the signal in this direction. So the window is not sliding, but the signal inside the window is going to slide. So when I'm going to slide on this side, this sample will get dropped, whereas new sample will come in. And when I shift this signal on this side, one will get dropped off the window and new signal will enter the window. Okay, so if I wanted to write x of n as, I write x of n as 1, 2, 3, 4, because that what I see inside the window currently. Suppose I delay the signal by 1 unit, then this signal will look like, now this 4 will go out, whereas I know there is a 4 the sample, or there is a sample with height of 4 present over here will take the 1's place. So the new signal that I will get is 4, 1, 2, 3. So I shift the complete signal, this sample got dropped and new sample came in the window. So it is 4, 1, 2, 3. If I advance the signal by one value, then I'm going to shift the signal this side. That time 1 will be dumped out of the window and the new 1 will come from this side. So I will get 2, 3, 4 and 1. Okay. Now this periodic signals normally is seen on a circle. It's like a clock. Let us say that I start my signal at 12 noon. So it is 1, 2, 3, 4. So this is my x of n. So this is my n is equal to 0 position. This is n is equal to 1 position. This is n is equal to 2 position. This is n is equal to 3 position. Now when I say that I'm going to shift the signal or delay the signal by 1, this whole clock is going to get rotated by one shift. So my 1 will come on this position, my 2 will come on this position, my 3 will come on this position, and my 4 will come on this position. So the new samples that I will get is 4. Okay, here it will be 4, here it will come as 1, here it will be 2, and here it will be 3. So the red sample shows the signal shifting. Okay, now when I advance the signal, let us say x of n is advanced by 1, not the red signal, with x of n. So this 1 will come on this side. That means I am rotating the complete circle once in the anti-clockwise direction. 4 will come on this side, 3 will go to 2, and 2 will come to 1. So I'll get 2, 3, 4, 1. That's a sample value. Okay, fine. Though this is circularly shifted, so sometimes this is called as circular shifting. Now, as we understood what you mean by a time shifting of periodic signal, let us see what is a time shift property of a DFT. So let us go for now for a time shift property. Now this is a circular time shift property, which is a fourth property. It says that if I have x of n whose DFT is x of k, and now I bring in a signal x of n minus L, okay, where L is the shift. L is the number of shift. In our example, it was 1, x of n minus 1 and x of n minus or plus 1. Here L is the number of shift. It can be 2, 3, any integer value, but it should be integer value. Then my x of k will be modified as x of k e raised to minus j 2 pi k L by n, right? So I'm shifting the signal by L times, then it is equivalent to multiplying the frequency by a factor e raised to minus j 2 pi k L by n. We know that Wn raised to 1 is equal to e raised to minus j 2 pi by n. Then we can write in terms of twiddle factor as n minus L is equal to x of k w n raised to, so x of k is equal to w n raised to k L. Okay, so I can replace it like this. So when I say that a time shift is equivalent to, okay, this I write as equivalent to multiplying by a phase factor w n raised to kl. We call it like this. So it is as good as multiplying by a phase factor of w n raised to kl. So as L will increase, this factor is going to increase. Okay. This is for n minus L. We can extend the idea to x of n plus L. Its DFT will be x of k w n raised to minus kl. Why I am saying this? Because if you observe, if there is a minus sign inside L, there's a minus sign over here also, and wn raised to 1 is e raised to minus j 2 pi by n. So now when I replace minus by plus, then this sign will also be plus, and then my w should be replaced 1 with the index. So I have minus kl in the index. Okay, so plus minus, okay, and minus plus. This you have to remember. So that is the formulation of frequency shifting property. Now, after time shifting property, let us go ahead with the fifth property, which is frequency shifting property. Now for frequency shifting property, if I have x of n as an input whose DFT is x of k, and suppose I shift the signal, I shift the k by L factors. So now I am shifting k by L factors, then the effect is the x of n will get a phase factor of e raised to j 2 pi, okay, n L by n, right? So if I am going to shift the frequency, it is as good as multiplying by a phase e raised to j 2 pi n L by n. Now here you can observe that when the sign is negative, here you have j sign as positive. But if I write in terms of twiddle factor, then it will be x of n w n raised to minus nl reflects x of k minus L. You can reverse way say it as multiplying by a phasor factor wn raised to minus nl, 2x of n will shift the frequency by L units. You can say in this fashion also. It is saying in the reverse direction. Okay, and suppose if I have x of k plus L, then its DFT will be x of n w n raised to plus n L. Okay, so this is what the two patterns of frequency shift property. So here you have to see that with respect to the twiddle factor, if I have minus sign, twiddle factor will also have minus sign. If I have plus sign, twiddle factor will also have a plus sign. Right? So this is a frequency shift property. Now let us go for the next property, which we called as complex conjugate property, which is a sixth property. So the complex conjugate property says that if I have my x of n, let us say f x of n is a complex sequence. For example, I would take x of n as x of n equals to 1 plus 2j, 3 plus 4j, 2 plus 2j, 3 minus 4j. Suppose such a way of x of n we have, which is a complex sequence, which is not a real sequence, unlike the one we have seen 1, 2, 3, 4. This is a complex sequence. And suppose x of n DFT is x of k, and if x of n DFT is x of k, then x star, that is a complex conjugate of x of n, results into x star of minus k, which can also be written as x star n minus k. So this is if we have an input sequence x of n as a complex number, and if I take its conjugate, then my frequency x of k will be shifted or will be mirrored and conjugated. So that is the complex conjugate property. Let us go with the seventh property. So the seventh property says about convolution. So let us have a convolution property. Now convolution property says that if I have x of n whose DFT is x of k, and I have h of n whose DFT is h of k, then x of n convolved. Now this is very important, this is always a circular convolution. H of n, its DFT is nothing but x of k into h of k. So rather than using a convolution complete big equation, we can just transform the signal to Fourier domain and multiply both of them. You will get the convolution of two signals. So that is a convolution of property. It signifies that convolution in time domain replicates multiplication in the frequency domain. Let us go with the eighth property. Let us say multiplication of signals or multiplication property. Again, if I have x1 of n whose signal is x1 of k, and I have x2 of n whose DFT is x2 of k, then if I multiply both of them, that is x1 of n multiplied by x2 of n, its DFT is x1 of k convolved, which is circularly with x2 of k. So we say that multiplication in time domain is equivalent to convolution, to be more emphatically saying that it's a circular convolution in frequency domain. So this is about the eighth property of DFT. Now let us go to the ninth property of DFT, which is correlation property. So the correlation property says that R of x, y of L, the DFT of correlation of x, y of L is nothing but x of k, y conjugate of k. Okay, so that is a correlation property. And the last and the final property is Parseval's energy theorem. So Parseval's energy theorem says that summation n is equal to 0 to n minus 1 modulus x of n mod square, its DFT is 1 by n summation k is equal to 0 to n minus 1 mod of x of k the whole square.